Let's get into some details about the observed MJO structures. Here again, all kind of processing is done before you do these longitude time Hofmüller diagrams. What is being shown here is OLR 850 hectopascal zonal winds anomalies and 200 hectopascal zonal wind anomalies. As you can see here, the period is October 1, 2003 to March 31st, 2004 as before. Colors represent the total anomaly from climatological seasonal cycles. So it takes out a mean plus 3 harmonics to fit the seasonal cycle, and that is determined for October 96 to September 2015. So the contours represent a projection of RMM indices onto these fields. For the zonal winds, contour areas are for full anomaly with the negative contours dashed, while for the OLR the contours are every 10 watts per meter squared beginning at 5 watts per meter squared with negative contours solid. So that is enhanced convection. Okay, so you can see that there is lots of noisy features in these figures, because when you do these processings, let's say you have a seasonal time scale, and then you have the sub-seasonal time scale, and then you have other higher frequency time scales which don't completely get removed. So you see lots of these noises, and then you draw these contours which almost seems like we are trying to fit something, but unfortunately that is the nature of the business. So here is negative OLR anomaly convective phase, and followed by, so we're going time this way, followed by dry phase, convective phase, and then maybe a dry phase, more well-defined MJO here with the convective phase and a dry phase, and so on. And you see corresponding figures, corresponding signals in 850 hectopascal anomaly, remembering that 850 is in the boundary layer, not necessarily at the surface. When we show those convergence divergence figures, we are basically saying there is surface convergence and there is upper level divergence, and 850 is not exactly at the surface, so we have to be careful about that. And you see approximately out of phase relations nonetheless between lower level winds and upper level, not out of phase, opposite direction, because you have convergence at the lower level and divergence at the upper level. But you can still see that the differences in the structures in terms of the zonal extents. Here you're going from 0 longitude to all the way back, so all those kinds of details. But these are the best you can do in terms of observations. And here is composite anomaly structure of the MJO by RMM phase for the extended winter, which is going from November to April for the seasons of 96-97 to 2013 to 2014, which includes the big El Nino and several other El Ninos that were more focused on the dateline. Colors show the OLR. Contours show the 200 hectopascal era interim geopotential. So we are using reanalysis products here, and the positive contours are green and negative contours are magenta for the OLR. No, for the geopotential, sorry. And so basically we see the same thing, upper level winds with the convective phase. Let's see, we are looking here at watts per meter squared shown here. I squeezed in the scale down here. So colors are the OLR. So again we are looking at the same thing as before. You can see these are upper level winds, so you have convective phase, negative OLR with divergence. So this is phase 1, phase 2, phase 3, and you can see the corresponding geopotential height signature. Convection would raise the geopotential, and dry phase would lower it, and so on and so forth. Just make sure you got the colors right. So positive contours are green and negative contours are magenta, so convection tends to be associated with positive contours and dry phase with the negative contours, which is what we expect. So just you have to remember again the propagation: phase 4, phase 5, dry phase ahead, divergence in the upper level moving with it, and by phase 6 you have the dry phase, the wet phase has propagated across, so you have a dry phase here. So the convergence in the upper level here, which means divergence in the lower level, and so on. So this is the observed structure, but this is now using era interim products, which can be considered as observations, but they are basically a blend of observations and models to reconstruct past variabilities. This is the same thing now for 850 hectopascal winds. So now you see again convergence and the convective phase. The contours show the 850 hectopascal era interim geopotential. Again, positive contours are green and negative contours are magenta. So which means now you see the structure here much more clear in the 850 hectopascal geopotential, as opposed to the Rossby wave signature here and the Kelvin wave signature here. Ahead of the convective phase you have the Kelvin wave propagating, and here you have Rossby wave signatures off in the tropical regions, not on the equator. So I think you can clearly see those here associated with the heat source. So the MJO related heat source obviously produces waves, but as we said, these are not free waves. They don't fit into that wave number frequency spectrum with respect to Rossby and Kelvin waves as we saw, but they are the same structure of Rossby and Kelvin waves, difference being that they move slower and they are convectively coupled. Okay, so this is another way to show it, where a base point is used in the Western Indian Ocean. So November to April lag longitude diagram of, so you have lag here from day 0 minus 5 pentads and ahead by 5, lead by 5 pentads. What are we doing? You're taking 10 degree north, 10 degree south averaged intra-seasonal, so that's 20 to 100 day bandpass filtered precipitation anomalies in colors and zonal wind anomalies in contours, against intra-seasonal precipitation averaged over the Indian Ocean, 10 degrees south, 5 degree north, and a longitude band of 75 to 100 degree east. So you're using a base point in, or a base region in the Indian Ocean, and starting with day 0, which is the peak of MJO convective phase, going 25 days before and 25 days after. So you are seeing the lead lag relations in zonal winds and precipitation with respect to the base region. So you can see here in the Western Indian region, the convection has moved ahead before the peak of this wet period here. Sorry, this is the dry phase. So you have dry phase ahead, convective phase propagating eastward, and then comes, after this has passed, you get the next dry phase. So here it is negative precipitation anomalies and positive precipitation anomalies, and associated with that you have corresponding zonal winds, and you can see the difference in the propagation of the rainfall and the phasing of the winds with respect to the convection or the precipitation. Okay, so that's kind of something that is not immediately obvious when we look at the composite figures of convergence, convection, and divergence above, and so on. So in this figure it's obvious that winds have much larger zonal scales than precipitation, and there is a phase lag in terms of converging zonal winds. So easterlies and westerlies behind, and then westerlies and easterlies. So you have to look for the correct phase that corresponds to convection and rainfall. This is the same thing, but looking for boreal summer months. Some people call them MJOs during boreal summer as well, but we will see that many of the interseasonal signals move northward into the Indian monsoon region during boreal summer. They are referred to as boreal summer intraseasonal oscillations. So you can see the structure is different here. Again, looking at OLR, geopotential height, and 150 hectopascal winds. So you are again looking at different phases, but instead of a systematic eastward propagation, you see these north-south structures and these tilting southeast northwest kind of structures, which we'll come back to when we look at mesos in a little bit more detail. So there are propagating interseasonal signals even in the boreal summer, and many of them do tend to originate in the western Indian Ocean, but as they propagate eastward, they tend to get detoured northward into the monsoon region, and you can see that the signatures are not as clear Kelvin waves as we saw before associated with the boreal winter MJOs. Okay, but that depends also on whether you have an El Nino. For example, during a strong El Nino, you still tend to get some MJOs that are going across, and maybe that has some relation to the fact that many El Ninos produce deficit rainfall. But there is a clear season of MJOs where it's peak during November to April, and mesos or monsoon interseasonal oscillations are peak during May to September, let's say. Okay, so again, when we say when we say in the boreal summer, they are not necessarily MJOs, but often referred to as boreal summer interseasonal oscillations. It means we still have many things to explain in terms of theories. Maybe I'll do this in the next podcast. This is already a long one, but we have to look at relation of MJOs with lower frequency climate modes, and we will see that that relation has some tempting information, but the relations are not totally robust or obvious. Okay.